Good morning and welcome to the 3.2 lecture video on derivatives of the exponential function. Sorry this is a little bit later than usual. I've been really busy this weekend, so hopefully you get a chance to watch this and take the video notes before Tuesday. So here's the warm-ups. First one is, here's a sketch of some function. Maybe it's an exponential function. No real scale here, so you can't get a very good sketch, but just based on the shape of this, what's happening with the slope of f of x, try to draw a graph of f prime of x and a graph of f double prime of x, the second derivative. Okay, and warm-up number 2 is just use some basic logarithm or exponent rules that you might know. If you struggle with these, don't worry about it too much, but just wanted you to remind yourself of some rules that you do know, how to simplify these exponential things. And for warm-up number 3, estimate this numerically. It means either using a graph or a calculator or something to estimate this limit. And so let's give these a shot and pause it right now because the answers will appear in 3, 2, 1. Okay, so here are the answers. So for the first one, if I'm going to draw the derivative of this, looking at how the slope is changing here, it starts off with a slope that's pretty close to flat, meaning the slope is pretty close to 0. And then the slope increases, so you have a more positive but still small slope over here, and then a bigger positive slope and a bigger positive slope. So when you draw a graph of that, it looks about the same. It starts off being pretty close, the y-coordinates are pretty close to 0, and then the y-coordinates get a bit bigger, but they're still small, and then they get bigger. And then when you do the same thing, it's going to have a similar shape of that graph too. So that's interesting. It looks like with a function that has this sort of shape, its derivative is going to have the same sort of shape. All right, so warm-up number 2. The rule for the first one that you need to use is when you have e to a power times e to a power, or anything to any power, and then that same thing to a different power, you add them up. Because it's like the total number of copies of A you have X copies of A and then Y copies of A multiplied together. So the total number you have being multiplied is X plus Y. And for B, when you have e to the t plus 2 times e to the t plus 2 times e to the t plus 2, and you add those all up, it's the same thing as doing e to the t plus 2 plus t plus 2 plus t plus 2, which is just the same thing as multiplying it by 3, doing e to the power 3t plus 6, which is what we got there. And then for C, this is based on the fact that the logarithm, natural log base e logarithm, and e to a power are inverse functions. That's the way the logarithm is defined. It's like the logarithm is a function where you input the result of some exponentiation, and the result of that is just going to be whatever that exponent was of e that got you that result. In other words, just x squared. It's a long-winded way of saying they just cancel each other out. And then for warm-up number 3, let's see. Okay, to estimate this limit, there's a couple ways you could do it. This first way I did is just I graphed it in GeoGebra. You could also use your graphing calculator or Desmos or something to graph this. So the graph looks kind of like this, which is y equals 1 plus x to the power 1 over x there. Let's think a little bit about this limit, because it's a weird limit. We're talking about as t gets closer to 0, that means the base of it here is getting closer to 0, but then the exponent 1 over t is approaching infinity. Well, it's approaching infinity from one side, and then it's approaching negative infinity from the other side. So how do we deal with this? Well, it's kind of like there's one thing making the limit get smaller, and another part of the formula it's pulling it in the other direction. Because if you had like 1.01, uh, let's say the limit as t approaches 0 of 1.01 to the power t, this would not exist because it would approach infinity. I'm sorry, I meant 1 over t here. It would the exponent would approach infinity, and that would make the whole thing approach either infinity from one side, and then it would approach 1 from the other side. So that limit doesn't exist. And if you have the limit as t approaches 0 of 1 plus t to the power 100 or something like that, well, as that just gets closer to the 1 plus t part gets closer to 1 to the power 100 is just going to get closer to 1. So it's like we have these weird parts of the function pulling it in other directions. Here, this part's pulling it towards 1, but then the 1 over t part is kind of pulling it towards infinity. So who wins in the end? Well, the answer is 2.7 wins. As you get closer here, let's zoom in. See what I mean by that. Try to zoom in here. Yeah, it looks like as our values of x get closer to 0 from both sides, then the function is approaching 2.71828 there, although you can't necessarily tell. It just looks like about 2.7 there. And then to get a little bit more precise, well, there's ways you could do it with a graphing calculator using the graph, or I'm just going to take a calculator and plug in some small values of t. So if t is 0.01, then the 1 over t becomes 1 over 0.01 is 100. So you get about 2.7 there. I plug in something slightly smaller, I get 2.717. And if I plug in a negative number that's even smaller, I get 1 minus 0.00001 to the power negative a million, and that's still 2.71828. So that's what this limit is. It's about 2.71828. Approximately. This isn't exact because we don't know exactly what it's approaching. So this is actually, you might have noticed by now, a good definition of E. The number E, which you hopefully know, is about 2.71828. Whoops. It's a really important number, especially for this section and especially for calculus in general. And we're going to see why right now. And I think it's really interesting because it's another of one of the most important numbers in mathematics, kind of like the number 1 or 0, in the sense that it just shows up in a lot of equations. Kind of like pi is a special one of these numbers. I think it's funny that this number is just a little bit less than pi. E is approximately pi minus 0.4. And okay, let's look at why it's so important in calculus especially. It's because of this fact, is that the derivative of the e to the x function is equal to itself. And that's what we saw, it looked like with at least the general shape of the graphs here. You can see it starts off flat, which means its slope is close to 0, just like the y coordinates here are close to 0. And then it gets steeper, and as it gets steeper increasing, the y coordinates are also going up. So they kind of go up at the same rate approximately as the slope. And let's see that with the other graph right here. So here's a graph of the f of x equals e to the x function here. If you plug in 0, the result is 1. If you plug in 1, e to the power 1 is about 2.7 here, so that looks good. And if I move this back and forth, remember that this what this triangle represents is this, you're getting the slope of this diagonal secant line, and the slope of that diagonal secant line is approximately equal to the slope of a tangent line about halfway between those points. So here at approximately x equals 1, it looks like the slope of the tangent line is about 2.8, which is close to 2.71, but you can't get it very precise with this rough estimate tool here. Here, if you plug in something around 0, it looks like the slope of the tangent line there is about 1. And as we go over here, the slope of the tangent line is getting closer to 0. And so, yeah, you'll notice that it looks like the slope here is approximately equal to the y coordinates that we're talking about. And you can see that happening kind of at all of these points. The slope is that number on the right, and it's approximately equal to the y coordinates of the points at which you're measuring it. So in other words, the derivative of this function is approximately equal to the function itself. So that looks like it could be right from the graph, but we're never really sure. So let's prove it algebraically using the limit definition of the derivative to make sure that it's actually exactly right, which is this. We have the derivative of the function is just the limit of this as h approaches 0 of e to the x plus h minus e to the x over h. And here the next step is we can factor out the e to the x from the top of this, as we'll see. So first step here, we just factored out this e to the x from the two terms in the top, which leaves you with the e to the power h, because e to the x times e to the h is the same as e to the x plus h. And there's also a minus 1 left over from that term. And then this is kind of a weird step here, because you might think that like e to the x is a function of x, so you can't just like take it out of the limit, but you actually can, because it's a limit as h approaches 0, but as h changes, x doesn't change. X is just like some value that we're talking about. It's like the point at which you're making the tangent line. So it's not changing as h changes. So you can actually use the limit law that says like you can just take out a constant multiple. And then you're left with this thing here. And what is this going to turn into? Well, let's use the definition of E here, which I made orange. E is equal to this limit as t approaches 0. But if we just think of, well, what if we just called this the same as the limit as h approaches 0, because it doesn't really matter what letter you use. So I'm just going to write this as the limit as h approaches 0 of 1 plus h to the power 1 over h. Oops, a weird sound. I don't know why it's doing that. But anyways, that way, because it doesn't matter whether you call it t or h here. And then in this step, we can just replace e with this definition as h approaches 0, because this is within a limit as h approaches 0, so it will look like this next step, where we just replace this e with the definition of e, which is this limit. And we can do that because we're already within a limit as h approaches 0. So yeah, that's just going to turn into e the closer you get. And then if you have a power to a power here, you just multiply those powers, and that just gives you the power 1, so it will simplify nicely, like so. And you're left with a nice limit here where you have a 1 minus 1, which cancels out, and then the h over h is just always equal to 1, so that limit is just 1. So yeah, so the derivative of e to the x using the limit definition turns out to be equal to e to the x. So that's why that works. All right, so here's a more general rule, which if you want to see a proof of it, I'm sure you can find it on YouTube somewhere. But the derivation for this is pretty similar to the last one. The only difference is if the base of your exponential function is some some other number, some other constant number not equal to e, then you have to multiply it by the natural log of a in front instead of it just being a to the x. So e is special because it's the only one where this becomes 1. And just to see a quick example here, let's see if you can use this rule to find the derivative with respect to x of e to the x. And let's do it now. I'll show you the answer in 3, 2, 1. Okay, so just using this rule to find the derivative of e to the x, I just mean using this rule just using e instead of a, and it works out so that you do the natural log of e times e to the x, because this has natural log of a, and the natural log of e is 1, just by definition of natural log, so it actually still works out to just 1 times e to the x, which is the same thing as the rule said before, the original basic rule of just e to the x. So yeah, it's good to just try to use more than one rule to do a derivative. It will help you understand the relationship between them. Now let's do example 2. A few more derivatives to try. Give these a shot. It'll take you a few minutes probably, and pause it now to do that, because the answers will appear in 3, 2, 1. And here are these answers. These ones were kind of tricky. Maybe I should have warned you about that. Anyways, if you got these, give yourself a big pat on the back. If you struggled with them for a bit and gave up, that's okay, because they were tricky. Anyways, just make sure you understand how these ones work. So the first one, well, first of all, this is a sum of two functions, and you can just take the derivative of the two functions separately using a theorem from 3.1. And that looks like this, but then these two functions, when you take their derivatives separately, look kind of the same, except they're different. And what's different is that the variable is x, in this one is the exponent, and in this one the variable is the base of the exponent on the right here. So when the e is about 2.7, if that's just staying at 2.7 and the x is increasing, then of course it's going to have a different slope, different rates of change than this one, which is going to be a very differently behaving function. Anyways, when it's e to the power of the variable, that's just the derivative we just learned about, but x to the power e is not an exponential function. Here the exponent is constant. We call this just a power function. It's x to a power. And then you just use the power function rule. Take the e down and the power becomes e minus 1. With this one, the trick is B, C, and D all have some kind of trick involved in them. The trick is that you can write this 3 to the power x plus 2 as 3 to the power 2 times 3 to the power x. And when you do that, and that works because 3 to a power times 3 to a power means just add those exponents, and it means the same thing. So, and the reason why that's really helpful is because then that 3 to the power 2 is also known as just 9 as a constant multiple. You can just take it out here and just do the derivative of 3 to the power x, and the derivative of 3 to the power becomes 3 to the power x times the natural log of 3, just using this rule, and that's what you get. No good way to simplify that anymore. Part C, let's see, the trick is with this one, so that we can use this rule to write it as something to the power x, is to notice that e to the power negative 3x is the same thing as e to the negative 3 and then to the power x. And that's so it's written as something e to the negative 3 to the power x. So then you just do natural log of that something times that a to the x, or e to the negative 3 to the x. And this is what you get when you simplify it, because the natural log of e to the power negative 3, the natural log and the e exponent just cancel each other out, and you get negative 3. And again, e to the negative 3 to the power x, multiply those exponents, and you get negative 3x. And with d, the trick is that e and pi are both constants. E is a little bit less than 3, pi is a little bit more than 3. If you do e to the power pi, it's about 23, and the derivative of that constant is just 0, because the derivative of any constant is 0. So that's the trick there. Let's go on to these practice derivatives using some of those same tricks as those last examples. Anything? Yeah, some of these are kind of tricky, but give them a shot. Do your best, and I'll show you the answers in 3, 2, 1. And here are those answers. So the first one, the trick is that the 1/3 is a constant multiple, so you can just ignore that and deal with the 3 to the x separately, which looks like so. We just have the 1/3 left alone times the natural log of 3 times 3 to the x. And then here, this is a power function. The dividing something by the square root of x is the same as x is times x to the negative 1/2. And then when we use the power rule there, we're going to multiply that 33 by negative 1/2. That's what you get. And then you get negative 1/2 minus 1 here. And that's what that looks like. With the second problem, the trick is this is a power function with x to a power that's constant. That exponent comes down, and then it becomes pi squared minus 1. And with this one, the variable is in the exponent, so it's an exponential function, and we use the rule for exponential functions, and we have the natural log of pi squared times that same function pi squared to the power x. And this one, we have the 5 times t times e to the t. Just write that as 5e all to the power t. That's the same thing. And then you can use the rule for natural log of I'm sorry, for something to a power. It ends up looking like this, where you multiply that function with this extra constant, natural log of 5e. And that's the end of that. This was a pretty quick section. Hopefully I'll have the other video for Tuesday up by tonight. I'm sorry if it doesn't get done on time. If not, we'll just have a regular lecture if there isn't enough time. But I'll do my best to get this done today, but lots of stuff is going on in my life this weekend, so I'll do my best. And have a good Monday and Tuesday, and I'll see you in class.